Welcome to this recording of lecture 20 of MCS 507. Today we are going to look into ordinary differential equations, and since this is a course on software, we are going to look very carefully in how this can be solved with the NumPy SciPy matplotlib. And in particular, we're going to see three applications of ODEPACK, which is available in the integrate module of scipy. So you see here that there are three subsections which are actually three times the same. So the three classical models we consider are an oscillating pendulum. Then we consider a model of celestial mechanics, and we end with the tractrix problem. So these are three classical examples of differential equations, and we're going to compute approximate solutions for the trajectories defined by the differential equations. Okay, so what is our first problem? We look at a ball attached to some cord, and it's oscillating back and forth. So the object is subject to gravity, and it starts in rest at time t, but with an angle theta that deviates from the equilibrium position. So it swings back and forth. So with Newton's law, the differential equation is written down here. So the alpha is a constant which captures the gravitational constant and the length of the rod that connects the sphere. So it's a second order differential equation. So there is the double prime there, and we want to compute the evolution of the angle with respect to time. Okay, so let's make a first attempt with scipy. So scipy cannot solve this if we would leave the sign in, but assume that we are working with small values of theta, then a first order approximation is to replace the sine of theta by theta. So this is a first order approximation. A higher order approximation would take more terms in the power series. So as always with scipy, we define the symbols, and we have to define theta as a function. So otherwise we could not write the derivative. So you see here we take the second derivative of theta with respect to time t. So if you would not have defined theta as a function, then this derivative would have yielded 0. Okay, so we define our equation. So here the alpha is not there like in the previous slide, so the L is multiplied out. So the equation that we are solving leads again to an equation. So here you see that the nice thing about the symbolic solution is that we see the two parameters in there, C1 and C2. So the C1 and C2 have to be defined using the initial position and the initial velocity. So C1 will be the initial angle, C2 will depend on the initial velocity. So this is a symbolic solution using dsolve from scipy. Okay, so scipy can solve this completely symbolically without using the initial conditions. If you want to do this numerically, that won't work. So we moreover have to rewrite the second order equation as a system of first order equations. So what does this system look like? At the left, we have the derivative of the variables. At the left, we see theta prime, and theta prime is the velocity. So at the right, we have the velocity, and the theta double prime, which was the acceleration, now becomes the derivative of the velocity. So using the interpretations of velocity and acceleration, you see it's very natural to rewrite this higher order equation, the second order equation, using an auxiliary variable, which is the velocity. Say that we have the initial conditions, pi over 6 is the initial angle at time equals 0, and the initial velocity is 0. So that would mean that we give our pendulum an initial deviation, and then we let it loose. Okay, so here is one method that we can define in numerical analysis. If you have taken numerical analysis, this then is very familiar. So we discretize the differential equation choosing a step size. So step size is here delta t. So delta t is finite. The h in the definition of the limit is an infinitesimal, goes to 0. If the delta t is well chosen, then we can take the approximations that we compute that way as approximations for the position, and then also likewise for the velocity. So the two formulas, the formulas are actually here. There are three formulas. We have a time stepping method. So we step forward in time. So we start at t equals 0, but then t1 becomes delta t. T2 becomes twice delta t. So this is this formula here. Then we have the angle that correspondingly also evolves. So the angle is computed then with this formula. So we have the differences, the forward differences of the angle, and then we compute the change in the velocity. Each time you replace the derivatives by the first order approximations. This is called the forward Euler method. Here, what does this then lead to? So we see the angle and we see the velocity. So this is a very simple model of a pendulum. There is no friction and there is no damping or forcing. So we have a very simple model, and thus the pendulum goes on forever, swings on forever. We see how the angle evolves and we see how the velocity evolves. Okay, so how do we do this now? We can program everything ourselves. So this is done here. So the pendulum is a simple differential equation, and our forward Euler method will work. So here is the definition of the function. So with the documentation string, what we give in as the parameters is the end of time, the t max, the number of steps, the initial angle and the initial velocity, and then the value for the parameter, the gravitational constant over the length, which is alpha. All right, we use scipy. So to compute the uh, arrays, so to initialize the arrays, so we will have a discretization of the step. So we have the number of steps and the length of the interval that then defines what in the formulas we called the delta t. We have our output. The output is the velocity vector and the angle vector, initialized with the initial velocity and the initial angle. And what this function does, it returns the vector of approximations for the angles, for the velocities, and then also the discretization for time, the time span. Here are the test values, and then with matplotlib we make the function. We make the plot. So we run the pendulum. We make a figure with two subplots, two rows. First row we have the angle, the evolution of the angle in function of time. In the second subplot we have the velocity. And that will give us the plot. Okay, so this worked. So this plot, which what I was showing here earlier. So this works very well for, say, a simple model like the oscillating pendulum. But actually, we would not want to do this for any differential equation. It's a bit cumbersome as well. So there is the odeint, which is the one of the main functions exported by a Fortran 77 ODEPACK library. So you can install this yourself, but the beauty of scipy is that this is all neatly wrapped. So there is some terminology there. So the initial value problem can be stiff, and that imposes a numerical difficulty. The odeint is capable of handling this. And the main difficulty in applying this routine is to figure out how to properly rewrite your higher order equation as a system of first order equations. Let's see how we do this. So we need to provide a function so that defines the right hand side. The left hand side will always be the derivatives. So what we actually are saying with the right hand side, what are the derivatives? So the higher order derivatives are actually replaced by first orders of auxiliary variables, very similar how we introduce the velocity. And that is done here. So we have a function of time, and the function takes on input a y1 and a y2, or a y0 and a y1, and it returns the right hand side. So the first equation expresses that the derivative of the first variable is here, the angle. So the derivative of the angle is the velocity. So the angle comes first, and then comes the velocity. So this is a two variable problem. So y1 is the velocity. So that's the first equation, simply stating the definition of our extra variable. So the second equation then states that the acceleration, or the derivative of the velocity, equals this sine function. And here 1/2 was taken for the alpha constant. And that's it. So once we have this, we can call the odeint after determining the parameters. So we work with a time span of 10,000 steps. We are running again, the initial angle is pi over 6, with an initial velocity 0. We have a time span vector and also a vector with the initial conditions. And that is it. So the solution that is returned is a matrix within the first column the values for the first variable, and then for the second column the values of the second variable. That is respectively the theta and the velocity. And that will give us the picture that we have seen before. Okay, so this is our running example. First, it's a non-trivial example, but it's a very simple example. The next example is less trivial. So let's look at a model from celestial mechanics. So we have three bodies. So it's not in space, it's in the plane. So to keep our model a little bit simple, but if you know how to write the equations for two variables, you also know how to write it for three variables. So the equations also are symmetric. So the bodies there are attracting, so they have their own gravitational forces that are acting upon each other. So the way there's also a second order derivative, a second order differential equation. So the way this happens is that the masses play a role in the numerators, and the distances play a role in the denominators. So the way the forces are going to act depends on the masses and on the distance between the three bodies. So, and I wrote down here on this slide the first equation for the first coordinate. There is a lot of symmetry, so we have the distances that are going to repeat it. So the numerators in the second equation, so the second coordinate for the first body, the denominators are going to be the same, but the numerators will differ. So instead of the x, you will have the y. So you compute the distance in the numerator of the first body to the second in the first term, and then from the first body to the third. So I explain it here for three masses, but it works for any number of masses. Okay, we have now a system of three bodies in the plane, so we have 6 second order equations. When we have to rewrite this as a system of first order equations, we are introducing the velocities in the both coordinate directions for the three bodies. So we are introducing 3 times 2 auxiliary variables, all the velocities, and we arrive at 12 equations, 12 first order differential equations. Okay, so what's so interesting about this? Well, there is periodicity. So there is a very strange orbit where you see here the three colors represent the trajectories of the three bodies. And they start each at different positions. But here I drew the trajectories just long enough so that the trajectories, you still see the three separate colors. So the red, the green, and the blue. But if the animation goes on for longer, the bodies will traverse each the entire figure 8. So this is a very strange and a very nice solution for this differential equation, for the system of differential equation. This is a nice model. Okay, so how do we do this then? Well, now we work with ODEInt. We have a vector now for 12 entries instead of the y with 2 entries from the beginning. We have a function of time. So what this function does, it returns the right hand side for the specific time value. So the numerical integrator of ODEInt will call this function all the time with specific values of time. So here for this experiment we take 3 equal masses. It's good for clarity that we have consistent naming. So in the naming we will have the coordinates immediately followed by the velocities. So you see the position of x1 is then the x-coordinate of the position of the first body is immediately followed by the first component of the velocity of the first body. And then the second component of the first body follows, the y component. First the position, then the velocity. So we use this relabeling to help us. What this relabeling does, it is essentially not strictly necessary, but it clarifies the code of the function. So we had the 6 original equations and then the 6 extra equations, which are essentially defining the relabeling. So we have that, just like we had with the pendulum, that the first right hand side is the derivative of the position, or it's actually the velocity, the first component of the velocity of the first body. That is expressed here in this first entry of this tuple assignment. And then once you know how to do this for one body, so for then we skip the entry, so then we have the velocity as well. But now for the second component of the velocity of the first body. So that's the third component in the right hand side. First body, second body, third body. And the advantage of this relabeling is that now we can work more correspondingly to the formulas. So we have to evaluate the denominators, and the denominators use the squares of the distances. So and here we compute all the distances. Now this is set up for 3, but it would not be too hard that if you have any number of bodies to make this way more general. Okay, so then the right hand side. So the masses were all actually 1, but it's good to define this a little bit more in generality. So the right hand side vectors now. So these are the original right hand side vectors. So the second component of the right hand side is the acceleration of the first component of the first body. So that was the equation that was defined on the slide in full. Well, here we now see the corresponding Python code. So the function that will be given on input to the ODEInt is now defined. Okay, so then we have to set up the specific positions and the initial positions and the initial velocities for this nice figure 8 picture. So what do we have? So you see that we have the third body that starts at 0. So there is symmetry. So the second position initial position is very symmetric to the initial position of the first body. And also the trajectories of the initial velocities are very specific. So there are very specific formulas for that. So we define then the vector of the initial right-hand side, and now it's important that we follow the convention that we first write all the data for the first object, for the first body. So the initial position, initial velocities for the x and then for the y. So these initial positions are x and y, initial velocities x and y. So we have these 12 initial positions. And then we define how far we want to go, what is our time span, how much we want to see. And then from the solution of the ODEInt, we extract the corresponding coordinates for the positions. So here I'm skipping the velocities. So I'm only plotting the trajectories. So the evolution of the velocities would also be quite interesting to observe. So that solves the problem. One has to be a little bit disciplined in the setup. For ease of coding, we can use the symbolic notation of the function, but for the rest, it's quite straightforward. Alright, an animation. We have essentially one parameter, and the parameter is actually the time span. So when we have solved our trajectories, we can start animating them. So what is computed by ODEInt, we will take a selection of this, selection of the positions of the three bodies, so the x coordinates and the y coordinates. So here they are selected in their entirety. So I did some relabeling. So the x coordinates of the three bodies, the y coordinates of the three bodies. So we have a number of frames. So the entire dimension, the dimension was I guess 1000. Is split up in a number of frames. So we don't want to have an animation that does this dimension long. So instead of having 1000 frames, I think I picked 30 frames. Okay, we set up the window. It's important here when you define the axis is that you kind of know where the trajectory, so that this is fixed. So in the animation, otherwise during the animation, the subplot window would be rescaled, and that would have some very strange effects. So we keep the window fixed. All right, and then it is a loop. And the key to defining this animation is that we have a frame parameter. The frame essentially determines what is the segment that is selected from the path. So the S1 x is the segment of all the x coordinates of the positions of the first body. So we plot these segments, we draw them on canvas, we pause a little bit, otherwise the animation goes too fast. So this is the code on the slide that runs in a Python script. I have a Jupyter notebook waiting, and I will demonstrate how this then also can run in a Jupyter notebook. Okay, we are halfway, 15-30 minutes in, so the timing works fine. So the last classical example is called the tractrix problem. So what is the tractrix problem? It's modeling a tractor trailer um, where there is a rigid bar between a trailer and a tractor. The tractor moves in a circle, and then we can ask what is the path of the trailer. Um, Here in this problem, we take a fixed bar of unit length, but this model can also be used for the predator prey, where we let the prey, and the prey is the tractor, instead of moving in a circle, the prey can follow any trajectory, and then the predator adjusts the direction. Um, where the prey is and either accelerates or uh, loses track of the prey. So this is a very fruitful model. So ultimately, so here in our application, we draw a snail. So the red shows the trajectory of the tractor. So the tractor starts at the right here, and the trailer, um, the bar is horizontally displayed here. So the progression of the blue bar uh, kind of illustrates how um, the trajectory goes, and now I must see that it went uh, counterclockwise. So you can see the green trajectory is kind of interesting. So at the very end, what actually happens is that the trailer ends up in the center of the circle. All right, what's the model? So the model is actually quite simple. It starts out with a first order system of differential equation. So it essentially states that the velocity vector of the trailer, so again, so there's an input and an output. So the input is here the trajectory of the tractor. So that's known, that's given, that's the circle. So what we want to compute is the path of the trailer. And in setting up the system of differential equations, we state that the velocity vector of the trailer has to be parallel to the direction of the bar. So it's logic. It's think about the predator prey. The predator moves in the direction of the prey. Here, the direction is the following the bar. So, and the bar is defined by the location of the tractor, which is given by x1, x2, and the trailer has coordinate y1, y2. So parallel means that it's a multiple. So the velocity is a multiple of these coordinates. All right. So what we will do with the velocity vector, now it gets a little bit more complicated to set it up. That's the reason why this is the third model. So there is something interesting going on here. So we normalize the velocity vector, and we compute the projection of the velocity vector. And that gives us the system of the first order differential equations. So just as we use these formulas symbolically here, note that this is all computed with numbers, given the coordinates of the tractor, given the current coordinates of the trailer. So we compute the right-hand side as this projection of the velocity vector. Okay, and then comes then the definition. So we have two functions. We have a function tractor in function of time. This will define the running on the circle, and I think here time goes up. So we indeed are moving counterclockwise. If you would work with negative times here, you would go clockwise. Then the trailer calls the function tractor. So the trailer will be passed to the ODEInt, but the trailer calls the tractor function. So in a way, this is nice to illustrate the flexibility of this uh, way of working with ODEInt. So you define functions that can call other functions. We use the linear algebra module to compute the norm. It's only here in two variables, could have been done explicitly. And then we compute the inner product as the projection. And that is the right hand side. So the right hand side is the velocity vector with the right hand side component. Okay, so then we have to solve it. So we call the ODE int. So to make the drawing, I'm actually then also running the function tractor on the time span. So I want, so in some sense it's a little bit overkill because we compute now the trajectory of the tractor twice. It was once called in the trailer, but the ODEInt will essentially only return the coordinates of the path of the trailer. So we have the trajectory of the trailer, so the X trail, the Y trail, and then the X track and the Y track. And we plot this, and this gave rise to the picture that we saw before. Okay, before I go to the exercises, let me try to switch to the Jupyter notebook. So here it is. So we have our first module. So in Markdown it is written here. So I'm restarting this lecture again. So recapping in quick to do the pendulum problem. So we have the model of the second order differential equation. So there's still a problem with this typesetting here. I will fix that later. So we have the equation for the pendulum. With the forward Euler here. So let me execute this. So I probably executed this already, but just to be safe. So this is our first computation running everything with the forward Euler. The celestial mechanics is a little bit more interesting. So we have the drawing of the figure 8. And perhaps I will go immediately for what I can show now is the animation. So here you see the key point of running an animation in a Jupyter notebook is that we have to add the inlining of the matplotlib. Otherwise it won't work. Okay, so I'm running this definition now. So for some reason it seems to... Okay, so here we are. And here you see the animation running in the Jupyter notebook. The speed of the animation is determined by this delay parameter here. So I pause, and perhaps let me do this a little bit slower. And now you see that there is more time, and you kind of see how also how the animation was built up by segments of the path, taking segments of the path. And one see clearly how nice this figure 8 gets drawn. And then it might also be interesting to look at the velocities. Okay, then finally we have the tractrix problem. So the tractrix problem is defined by the trajectory of the tractor and the trajectory of the trailer. So the last picture is shown here, and I leave this probably as better as an exercise, but it would be a good exercise to make also an animation of this. Okay, so let me move back to the final slides. Um, okay, so ordinary differential equations are important. So in a way, in the second week of this course, I introduced NumPy, SymPy, SciPy, Matplotlib. So with NumPy we have numerical linear algebra. The numerical solving of differential equations is also very, very important. So in a way, in the design of the course, this could have followed immediately after the NumPy and SciPy stack as a third lecture, but the second week of classes was a short week, so that's why this got kind of truncated. There are some exercises. The most interesting one I suggested, an interesting one already, I suggested the animation for the tractor, the trailer. If there are some interesting exercises as far as coding wise goes, so you can look at many bodies simulation. So ultimately, this could be used for a simulation of the solar system. So that would be a very nice project. Or you can look for actual data of the system of the Earth, Moon, and Sun, or a satellite and Earth and Moon. So there are some modeling projects here. Then there is the predator-prey model. I did this here in SciPy, in the NumPy, SciPy, Matplotlib stack, but there is also ample documentation in Sage of ordinary differential equations. So the question is it easier in Sage than doing this the way it was explained in this lecture? Okay, so this lecture is still more towards the beginning of the course, but it's also a nice illustration of animations, also a recap of what we have done thus far in this course. So I hope this lecture was interesting. I thank you for watching.